Hello. This is a quick video to go over some of the questions that were asked regarding the Unit 2 review on conic section sequences and series. So we're talking about workbook pages 217, 218, 219. Quiz 4, which about half of you guys came and picked up yesterday, so hopefully going over that is helpful for you. Is going to be the bulk of the quiz this Friday, although, when we would give a full exam, it was probably about 70% of the exam. I think it's about 60% of the quiz since you've already been quizzed that. So about 40% of the quiz is going to be conic section apps, and then some sequences and series. You have to know the sigma notation to do those, but that's kind of the breakdown. So a lot of the quiz coming up on Friday is stuff you've already been quizzed on, and the other chunk will be stuff that we went over last week and have been reviewing this week. You've already seen these answers, so I'm not going to spend a ton of time going over them. These were all attached to the PDF that was put out yesterday around noon. And so hopefully you've either checked these using your phone or your computer, laptop, Chromebook, whatever, or at least printed them off and then kind of gone over them. There were 5 questions that were presented to me, and those are the ones I spend some time kind of walking through and explaining. Hopefully that'll help out some folks who were getting stuck. The first question that was asked was a conic section question, and it was problem number 12. So here is all the work shown, but I'm gonna try to go through it and explain these steps for you. Okay. The first thing I'm gonna do is try to figure out what type of conic section this is. I know from looking at your quizzes, a lot of you guys were using the A times C formula, where if you multiply A and C, you either get 0, a positive number, or a negative number. And depending on what it is, that will tell you what kind of conic section you're looking at. In this case, A is 2 and C is -3. And that's fine. That works well. Usually I don't worry about the value of A times C, but really just what A and C are. So if there is only an A or a C, if there's only an x squared or a y squared, I know that it has to be a parabola. But since there's both an x squared and a y squared here, it's either going to be an ellipse, which might be a circle, or a hyperbola. The fact that the x squared is positive and the y squared is negative, so these guys have opposite signs, that tells me this is a hyperbola. So first thing, identify what we're working, okay? Now that I know it's a hyperbola, I know I'm gonna have to do some completing the square. So I want to do some organizing. On the quiz, there were a couple people in each class who went straight from the problem to this step, which meant that you were commuting the terms and factoring simultaneously, which you're not allowed to do. That's 2 different operations. You can't do those simultaneously. So just commute the stuff. Move the x's together, move the y's together, move the constant out of the way to the other side. That's the first thing. And then we can go ahead and do some factoring. So from the 2x squared and the -12x, I can take out a 2. And that's what we did right here. And then this is a mistake that was made by probably about 1 out of every 3 people on the quiz. I see that I have a -3y squared and a -24y. I'm going to take out the -3. And what a lot of people forgot is that when you divide a negative by a negative, right? -24 divided by -3, I get a positive. And so that gives you the opposite value for part of the center of this conic section, and that kind of gets you off on the wrong foot. So it's just an algebra mistake, and it's easy to make, but you do these again and again and again, especially on the hyperbolas where you know that you're going to have a negative term. You really got to look out for that. When you factor out a negative, you're going to have to, divide the negative by the second term also. Now that sets us up to complete the square. Time to complete the square. Half of 6 is 3. 3 squared is 9. But 2 times 9, right? Don't forget, multiply, a couple people did, is 18. Half of 8 here, half of 8 is 4. 4 squared is 16. But I'm not going to add 16 to the other side because it's really a negative 3 times 16. I'm really subtracting 48. And so I have to subtract 48 over here, okay? Now look what happens. We end up with a negative 90 when all is said and done. That's kind of not what we're used to getting. We're not used to getting negative values over here. You could immediately fix that problem by multiplying both sides of the equation, but through by -1, and that would fix it. But I just kind of divided by the negative 90 instead, and we ended up fixing it a couple steps down. So we divide by negative 90 because we have to have our conic sections equal to +1. The 2 over negative 90 reduces to negative 45, and the 3 over negative 90, and I guess it's really a negative 3 over negative 90, reduces to a +30. So what we find out here at this point, right, is that it's not in the traditional form that we like to see it in. We have the negative fraction first and the positive fraction second. We don't like that. I mean, technically, I guess you could leave it that way as long as you understood how to interpret it, but we like to see the positive first. So all I'm going to do here is just use the commutative property and move the positive fraction to the front, the negative fraction to the second term so that it can be subtracted. And that's it, okay? We can now interpret what we're looking at. We're looking at a center of +3, -4. Okay, that's where that center is. Looks like the a squared value is 30. And the square root of 30 is going to be between what? The square root of 25 and the square root of 36. So it's going to have a value between 5 and 6. 30 is just a tiny bit closer to 25 than 36. So it's going to be just a tick under 5.5. So as long as you put your vertex, just a little, basically between 5 and 5.5 units away from the center, you're going to be in good shape with that accuracy. The square root of 45 is between root 36 and root 49. Definitely closer to 49 this time. So we're going to be closer to 7 than we are to 6. And if you put your b value, greater than 6.5 but less than 7, you'll get credit for that. Now, some people did get the a squared plus b squared versus a squared minus b squared equations confused on the quiz. For ellipses, it's a squared minus b squared. For hyperbolas, it's a squared plus b squared. And so, a squared is 30, b squared is 45. 30 plus 45 is 75, which is between root 64 and root 81. So we're talking about a focal length that is greater than 8, less than 9. 75 is a little closer to 81. So I think we're going to be just a little bit closer to 9 than we are to 8, maybe 8.7, 8.8 right in there. Okay. And that's where the values come from. Because the y squared is positive, this guy's going to open up and down. That is definitely a mistake that was made by probably not half, but pretty close to half. I bet 40% of the people on, well, yeah, maybe 30% of the people on the quiz got the hyperbolas going in the wrong directions. If the y squared is positive, it goes with the y-axis up and down. If the x squared would have been positive, it would have gone left and right with the horizontal focal axis. But that's why this guy opens up and down. I use the A and B values to create that that asymptote rectangle. Some of your graphs were really good on the quiz. Some of them were a little sloppy. You probably would want to use a straight edge. And yeah, that's problem 12. So hopefully for those who asked for problem 12, that helps you understand this problem a little bit more. I'm going to be real honest with you. Now that you guys are trapped onto taking assessments on a computer, there's really not going to be any way for you to graph these anymore. So you would have had like double the graphing questions. You had 2 on the quiz. I think it would have been 4 if you actually took the legit exam that we would traditionally take. That's just not where we are anymore. So you're not gonna have to sketch these anymore, but you're definitely gonna have to continue to be able to identify the important characteristics, the directions of the graphs, and pick, given an equation what the graph would look like, or given a graph what the equation would look like. Those types of problems are definitely going to continue to be important. Number 13 was another general form equation. We had to put it into standard form. This time it only had an x squared, no y squared, so that meant it was a parabola. Okay. All right, and then we got into applications. Nobody asked any application problems, so that's, there's probably going to be a couple application problems on the quiz on Friday. Sounds like you guys are in good shape. This one was the parabolic or paraboloid problem, where the beams were bouncing off the dish and going straight to the focus. We used the general or standard form of the parabola with a point to figure it out. This was the elliptical application problem, and it used the orbit of Saturn to find the aphelion and perihelion. The aphelion, remember, is the longest or furthest distance in an orbit, and the perihelion, the closest. And then the last question was that crazy hyperbolic orbit problem. And these is definitely the ones that's the most work, where you have to set up a system of equations, do some substitutions to get the answers. And nobody asked this one. So good job. I mean, I know you've probably done about 3 or 4 of them now, and maybe you're getting used to them, but that's great, because these definitely have a couple steps to them, and if you guys didn't ask, then you're in good shape. This is actually the one we did in our notes, right? If you go back to your workbook and look at the notes, and you can see that the numbers changed, but all the equations and the steps are absolutely identical. And then we did 2 more out of the textbook last week, I think. 17 was a problem where we were just expanding the sum, and that's how that one looked. It didn't say to evaluate the problem, so once I kind of simplified my fractions a little bit, I was done. If it said to evaluate, we would have had to actually get a common denominator and add those together. Number 18 was another just summation problem. 18 was actually one that was asked, so we'll spend a little bit of time with this one. I honestly think that what confuses some people on this is that you have like a little n on the bottom, right? And a big N on the top. And I think that just messes with people. I didn't write this problem, so I really don't know what the intention was, whether it was a typo or whether they actually wanted people to have experience with this. But little n and big N are not the same. They are they're definitely different variables. And so we're starting this this series at n. So if I plug an n in, you know, I get n plus 1. And then after n, I get n plus 1. But n plus 1 is n plus 2. And then after n plus 1 is n plus 2. But when I plug n plus 2 in here, I get n plus 2 plus 1, which is n plus 3. So that's where the n plus 1, n plus 2, n plus 3 comes from. Now, if it was a little n plus 3 up here, I would actually just have one more term. N plus 3 plus 1 would be n plus 4, and that would be it. I'd have 4 total terms, and it would be over. But because it's a capital N, it's a different sequence. And so the very last term is going to be capital N plus 3 plus 1. And of course, 3 plus 1 is 4. But 1 less than n plus 3 would be n plus 2. And n plus 2 plus this 1 here, right, is n plus 3. You don't really actually have to do 3 at the beginning and 3 at the end, but you do have to do at least 2 at the beginning, at least 2 at the end of these finite series where we don't know exactly how many terms to establish the pattern that's occurring. I like to do 3 at the beginning, 3 at the end, but if you do at least 2 at the beginning and 2 at the end, you'll be okay. Hopefully that explains this one a little bit more for the student who asked for number 18. Number 19 was an arithmetic sum, right? Just a linear pattern. This one's going up 5, up 5, up 5. So we get 5n minus 13. Some people are still kind of getting a little stuck on, you know, where this value is coming from. Well, remember, we always start at the first term. We always start at term, you know, at term number 1. And so if I know the slope is 5, it's going up by 5, 5, you know, plus 5, plus 5. I know there's a 5n in there. And I know that 5 times 1 is 5. But my first term is not 5, it's negative 8. So how do I get from 5 back to negative 8? And that's where you figure out what that adjustment factor is, minus 13. 20 was actually the one that was asked, though. And I definitely find that these geometric series continue to really be confounding to quite a few people. And I think if you can get yourself to realize they're really all the same, that you'll be way, way better off, okay? They all are just going up by the same, or down, I guess, if it's a fractional multiple, but up or down by the same multiple, times negative 2, times negative 2, times negative 2. The common ratio, we call that R, is negative 2. And once you know that, you can write these equations really quite simply. So let's go ahead and do that. I'm gonna write the pattern here for you guys. This is the general pattern, okay? It's A1, so that's the first term, multiplied by R, that's the common ratio, to the n minus 1. So this is in your notes in your course pack. Hopefully you kind of highlighted it when we were going over it. But this is the one you're going to use every time. So the first term is just a 4. And the common ratio we already said, to get from 4 to negative 8, I had to multiply by negative 2. To get from negative 8 to positive 16, I had to multiply by negative 2. The common ratio is negative 2. And that's where this formula comes from. And getting this formula, you know, is half the battle. We now have our formula, and that's a big step to being able to solve a geometric sequence. Okay, that's where this dude right here comes from. Okay, now I need to know how many terms there are. These problems didn't actually ask us to find the sum. It didn't actually ask us to evaluate the series, but it did want us to write the sum in sigma notation. And And that means we need to know how many of these terms there are. We know we start at 1, but how far out do I go? So where does this 10 right here come from, right? So this is the work that you have to do to figure that out. You take the formula that you just created, right? And you set it equal to the last term. Now, I did something here that may be confusing to some folks. We talked about this in the notes last week, or I guess before break. Um, we take away the negative ratio with one of these alternating sequences, and we also, if the last term is negative, take away that negative. And the reason is because I'm going to eventually have to convert this into a logarithmic expression, and I can't have negative bases within my logarithm, right? And I also can't have negative arguments because those produce undefined values. I can't have them. So all I'm doing here is pretending that everything's positive to figure out what n is. Once I know what n is, then I can go back and use my regular, alternating negative ratio to get the rest of the answer. Let me try to expand on this idea just a tiny bit for those who still might be confused, okay? I'm just going to pick a nice, simple ratio. Actually, let's use the same one. Let's say that we're doing, 4, and then double that is 8, and then double that is 16, and then double that is 32, okay? And then we keep going. So I want you to compare the alternating sequence, which we actually had, that was going negative, positive, negative, with this one. That's just straight out back and positive all the way through. What I want you to realize here is that it doesn't matter whether the values are positives or negatives. The absolute value of the terms is going to line up every time. The first term is 4. The second term is 8. Now, one of them is being added, one of them is being subtracted, but 8. The next term is 16. The fourth term is 32. Now, one of them is being added, one of them is a negative, right? But 32 is still the fourth term. And so what I can do is I can just turn everything into positives to solve for how far out in the pattern I am. And then I can, turn back the negatives on to actually get the answer. This one didn't actually ask me to go that far, but that's why I got rid of the negatives. You can't have negatives in certain parts of logarithms. So anyway, let me explain these steps to make sure you're good on them. Step 1 here, what I did was I set the pattern equal to the last term, as we discussed. Step 2, I divided by 4. I'm going to have to turn it into a logarithm. I need to get rid of that 4, so I just divided both sides by 4. Now it needs to be converted into a logarithm. So the base of my logarithm is 2, right? The exponent is n minus 1, so that goes over here, and then the argument is the 512, so that's what goes into the argument, into the logarithm. And now we've converted it. Now, if we were taking these tests in class, you would be forced to go into press the test mode, and you would not have access to the logarithm buttons on your calculator. I'll remind you of this here really quickly. So I'm going to pause this while I open up the calculator. Hold on. All right, it should be just about ready to pop open for us here. And then I can kind of remind you some things that we were talking about. Well, I thought it was about ready to pop open. There we go. Boom. Don't need that, do we? Perfect. So we are basically taking the log base 2 of 512. Now, if I put you into press the test mode, you would have no option but to use the change of base formula and do the natural log of the original argument divided by the natural log of the original base to figure out that that's 9. but you'll be taking these tests in a situation where you're not going to have to put yourself into press test mode. You can just type in log base 2 of 512. And so it would actually look like, where did my calculator go? There it is. I'll just go to the log template over here. And it's looks like the sixth one in. Okay, so log base 2 of, what was it, 512? I hope that was right. And yeah, 9. So there you go. 9 is what we're looking for. So you guys could probably do these problems a little more efficiently without having to use change of base. Now, don't forget that we're actually solving for n minus 1, right? And so once you do this, you have to add the 1 back over. I added it over on this step. You could have waited until the last step, but that's where the 10 comes from. Okay, so for those of you that asked for number 20, that's probably more answer than you wanted, but hopefully that was helpful for you. 21 is finding the value of a sum, and it's a linear. Now, nobody asked this one, but just really quickly, if you tried to use our formula on this one, since it's linear, since it's arithmetic, you could, but you'd have to make an adjustment, because notice that our value is not starting at 1, right? So you could plug 4 in to our formula to get the first term. You could plug 9 in to get the last term, because the formula is n times a1 plus an equal to 2, right? And so you could plug in 4 and 9 to get a1 and a2, but what about the number of terms? Well, it's not 9. 9 is the last number we plug in, but remember, we didn't start at 1, we started at 4. So there's actually 6 terms from 4 to 9. And so you could still use our formula, but I just kind of plug them in. So be careful if you don't start your sums at 1. Our formulas have to be adjusted. Now, there was a question on number 22 here, and it might have been because somebody was trying to use one of the formulas. But remember, the only 2 formulas that we're working with are arithmetic, which means they're linear patterns, first degree, or geometric patterns. Geometric are like exponential patterns, where the variable is in the exponent. This is neither. This is a second degree equation, isn't it? With the squared. So this is a quadratic. And there are ways you could do this, but that's not one of the things we're covering. So you really have no way of doing this using a shortcut method. So we're just going to do it slowly. Now, that's why they didn't give you like 10 terms or 20 terms. They only gave you 4 terms. So we're going to start with a 1, okay? And we're going to plug a 1 in. And then after 1, excuse me, comes 2. And so we're going to plug a 2 in. And then after 2 comes 3. So we're going to plug a 3 in. And then this summation statement tells me to stop at 4. So I'm going to plug a 4 in. And then you have to follow order of operation. You have to do your exponents first. So I squared all of those terms. And then you can do your multiplication. And then finally, you can do the subtraction that they wanted you to do. And at the end, you just add them together. And you're done. I think the -2 and the 2 cancel out, and 12 plus 28 is 40. So if you were the people that asked about number 22, hopefully that explains it. You might have just been getting stuck on the fact that it had to fit one of our formulas, but it doesn't fit one of our formulas. It's a quadratic, and we didn't do specific formulas for quadratics. Now, the last one that was asked was number 24, which once again is another geometric. 23, nobody asked. It was another arithmetic sequence. It was going down by 3 each time. So the slope is like -3. And then, to make the adjustment, I had to add 5.5. And there you go. 24 is the one that was asked by quite a few people. And once again, you have to know how to build the formula first of all. So that's what I'm trying to show you kind of in this little section right here. You always start with the first term, which is 2. So that's where, that's where this comes from. First term. And then how am I progressing through? Well, I'm multiplying by 3, I'm multiplying by 3, I'm multiplying by 3. And so that's where the 3 comes from, is by that common ratio. And then it's always to the n minus 1, because our formula likes us to start at 1, okay? And that's it. That's where the formula comes from. Now, I'm pretty much done. I've got this, I've got this. The only question is, how far out do I go? And this is usually the part of the problem that requires the most work. We need to figure out how many terms out the last term, 39,366 is. So what I did is I set 39,366 equal to our formula. I divided by 2. I converted it into a logarithmic equation. The base this time is 3. The argument is 19,683. Traditionally, you guys have to use the change of base formula to do this. And I've got this puppy like growling at me here. But you guys don't have to do that. You guys should be able to enter it just like this. Log base 3 of 19,683. Let's try that out. Maybe. Log base 3 of 16,983. Did I get that right? Nope, I didn't. 19,683. 19,683. All right. So there we go. And there you go. We get 9, which is, what we got down here. We got a 9. And don't forget to add 1. Don't forget to add 1 to solve. Now, this is the first one where we actually have to use our summation statement. So let's talk about that for a second. It is this formula right here. The first term multiplied by 1 minus the common ratio to the nth power divided by just 1 minus the common ratio. It's really just a formula. And you just have to plug the numbers in and then be careful when you enter it into your calculator. So what I did is I looked at the pattern up here and I said, oh, the first term is a 2, so I'm gonna start with a 2. And the common ratio, we found was a 3, right? So I'm gonna put a 3 here and a 3 here. And then the hardest part to solve for, is how many terms there are. That's what we had to do over here, right? Solve for n. And so that's where the n goes. And then it just comes down to plugging it in your calculator. I mean, I think technically you could plug it in just like this, okay? As long as you were careful with, making sure everything matched up. If it was a negative common ratio, you do have to use parentheses sometimes. But 1 minus 3 on the bottom is pretty easy to simplify, and then the 2's cancel, right? So you just have that negative left over, and then you just have to do 1 minus 3 to the 10th, and then take the opposite sign of it. It works out pretty easily. There were a couple of you guys that asked for number 24, and I hope that helps. Now, any of these questions that maybe my explanation wasn't thorough enough or still left something that you didn't understand, or even if you found another problem that you were getting stuck on that you didn't ask about, remember that I'll be hanging out at 3 o'clock tomorrow. You don't have to stay for a long time. You can pop in and ask a question and then get out of there within 5 minutes. But Let me know if there are any questions tomorrow during the help session. I'm going to try to put together a solutions guide for the quiz so that those of you guys that pick those up can look over the answers and to see if you can understand the problems you missed. You can ask about that tomorrow during the help session also. Have a good one, and good luck studying Thursday. Thursday is really just a study day, going over the problems you've done, studying your formulas, your notes, and getting ready for a quiz on Friday. Friday's quiz probably isn't going to be any longer than what you took, on quiz 4 before we left school. Some of you might even think it might end up being shorter, but it's going to be different format. And just taking a quiz on a computer is different than in paper. So do a good job preparing on Thursday, and then on Friday you'll be ready to go. Let me know if you have any questions, and good evening or good morning, whatever the case.